All right, folks. Over the next few sections, what we're going to be doing is introductions of how to kind of graph functions without even knowing exactly what they look like. So this first one, obviously, I know it's a quartic. The second one, I know it's a square root or a parabola, right? Downwards quadratic. That's a rational function. That's a quartic. But maybe I don't know what 2t ln of t looks like. I kind of have an idea in my mind, but maybe I don't know. And we're not going to get into that today. We have a few things that we need to cover throughout notes while we do that stuff. But all of these characteristics that we're going to go over in the next few sections is going to help us be able to do something called curve sketching, which is essentially just being able to graph the function using derivatives in calculus in order, words. It's too early in the morning for me. It's only 8 o'clock though. Anyways, but using characteristics from our calculus concepts to help us graph functions. Okay, so this first one, we are going to get into something called the extreme value theorem. Essentially, it's kind of silly, but it is a theorem. Not silly, but it's just pretty straightforward. Essentially, it's saying, given an interval from A to B, and say I have two different points or whatever, as long as it is continuous, then this has both a minimum and a maximum point. The minimum here would be that value. The maximum here would be that value. All right, so as long as it is continuous, it has both a minimum and a maximum. Also notice that this is a closed interval, which means A and B are both included on the graph. The reason that that is important to note is because a graph like this actually has no minimum, no maximum. Yes, it kind of ish does, it approaches values, but there's nothing that we could actually define to be the minimum or the maximum point. So know that if you have like an open interval, we don't define anything to be a minimum or a maximum. You could write it as like a limit, I guess, and I don't think that is blasphemous, but there is no exact number that is the minimum or the maximum in this. What else? Okay, and we do have something called a relative and an absolute. So if I were to look at a graph like this, say I have something like this. This is a concept we did in pre-cal. I have two maximums. Both of my red points are maximums. This point here is called a relative or a local maximum. This point is both a local and a global. Is how you could see that written. You could also see this as relative and absolute. Right, so out of my graph all together, this is the highest point. There is no other point higher than that one. So that is the absolute max. That is definitely the highest point. You could also see this listed as the global max, right? Out of the whole world of this function, this is the highest point. It is also a local maximum. It is a local maximum because with the things just relative around it, things right around it, it is the highest point. Which is the reason that this point is just a local maximum or a relative maximum, because of the things just around it, it is the highest point on the graph. So just like we have local maxima and global maxima, we also have local and global minimums. So this would be a relative min, and this would be an absolute min. Absolute is global, relative is local. I mean, it kind of makes sense, right? Relative is usually like relative to things around it. It's only talking about a small portion of it. Global is talking about huge, so that would be the absolute part. All right, so that's our main concepts. Now we're going to get into this stuff. So find the extrema on this interval. And one important thing to note too, we've talked about this, but it really comes into play in this section, is our horizontal tangents, right? I have a horizontal tangent here, and I have a horizontal tangent here. So notice my maxes and mins happened at the endpoints, so that's one place that we're going to have to check for maxes and mins. I also have to check any time that I have a horizontal tangent to see if that is a max or a min. We're going to get into something in just a little bit called something the first derivative test, where you can verify that this is a max and min. But for now, we're just going to trust that it can be. All right, so we need to check two places. We need to check our endpoints, and we need to check the places where we have our horizontal tangents. So for finding the extrema on this interval, it's pretty easy enough to recognize that, yeah, I need to check A and B. I'm going to need to check -1 and I'm going to need to check 2. But I also want to take the derivative. Good morning.
Good morning. Are you on a call right now?
I am making a video. No, you're fine. All right, so there's my derivative. And I need to find the horizontal tangent, so I'll set that equal to 0. And I'm going to go ahead and factor out 12x squared, because why not? Save some time. All right, so I get to this point. So I notice that I have solutions, or horizontal tangents, when x equals 0 and x equals 1. Those are both within my interval, so I want to check those values as well and see what they are. So now, to check the extrema, f of -1, do the plug-in thing, right? So I have 3 plus 4 would be 7, and f of 0 would be 0. F of 1 is -1, and f of 2 I need to do a little bit more work for. So 3 times 2 to the 4th is 16, 2 to the 4th, and 4 to the squared is the only one that you can like write the base as the exponent and vice versa, and it'd be the same thing. Fun fact! Alright, so that's 48 minus 32. So that is 16. So it looks like for my extrema, I have a local max, right? So thinking about this graph, I'm going from -1, 7 to 0, 0 to 1, -1. Is that part right? Yeah. And then to 2, 16. So maybe that part in the middle isn't actually an extrema at all, right? So if I'm thinking about my graph, it had to go through here, and this would be a local max. This would be nothing in the middle. This is a global min, or an absolute min. This is a global max. All right, and don't forget our globals are also relatives, or locals. Either way you want to say that. Right? So I would list off to the side, and I would say a local max at -1, 7 and 2, 16. A global max at 2, 16. And a local / global min at 1, -1. Right? Right. All right. And the other thing you can do is if they're asking for the values, so this one I did not ask for the values, but if they're just asking for the values, all that the values are is the y values. It's just the outputs that would be your max and mins. So just pay attention there. If we have the word values, we're just looking for the actual values. Okay, found the absolute extrema on the closed interval. So I'm going from -3 to 1. So again, I'm going to want to check my endpoints as well as when my derivative is 0, which my derivative is 0 when x equals 0 here, and that is within my interval. So let's see, f of negative 3 is 5 minus 9 is negative 4. F of 0 is 5. F of 1 is 4. So I needed to go from negative 4 to 5, and then from 5 to 4. So I know that this is a min, this is a max, this is also a min in this case. But for the absolute extrema, notice it just says absolute. I do not want to list that 4 as a minimum. So I have an absolute max at 0.5 and an absolute min at negative 3, negative 4. All right. So here again, I'm going to want to check my derivative. So g prime of t would be low d high, so t plus 3 minus high d low, all over low squared. Which would be 3 over t plus 3 squared. All right, in this graph, I know what the graph of a rational function looks like. The graph of a rational function looks like 1, 2, 3, and my horizontal asymptote is 1. And if I put in 0, it is 0. So my graph is going something like this. Right? And so from negative 1 to 6, there's really not going to be any horizontal tangents for this. So really, I just need to check the endpoints. So at negative 1, what is my value? At 6, what is my value? And then that's going to be my absolute max and my absolute minimum there. So g of negative 1 is negative 1 over 2, so negative 1/2. G of 6 is 6 over 9, which would be 2/3. So this would be my absolute min and absolute max. So absolute min. Here, let's say if we were doing the value, absolute extrema value. So in this case, if it's just asking for the absolute extrema values, all I'm going to be putting is that there is a minimum is negative 1/2. The max is 2/3, right? So it's asking for the absolute extrema. So what is the highest? What is the lowest point? It's implied that these are global because that is what they are asking for. So the minimum is negative 1/2. The max is 2/3. Notice it is just the values, not the points in this case. Okay. So next thing we're going to get into, and last thing for this video actually, is something called critical numbers. These are going to be really, really important as we move forward. They are solutions when the derivative is equal to 0 or it is undefined. So that's really all that we're going to be looking for. So we're looking for horizontal and vertical tangents, right? Vertical tangent is when my derivative is undefined because I have a up and down line. Okay, so finding the critical numbers, all I need to do is find the derivative. So 4x cubed minus 16x. Then I will factor out and set it equal to 0. A 4x, then I have x squared minus 4. So I have 4x times x plus 2 and x minus 2. So my critical values, or critical numbers, are when x equals 0, negative 2, and 2. That's it. Those are values that we're going to need to do stuff with. Okay, so same idea. Find your derivative. So we got to use the product rule, 2 ln of t, and then plus 2t times 1 over t, which will simplify to 2 ln of t plus 2, setting it equal to 0 so I can subtract 2 and divide by 2. So that's negative 1 equals ln of t. So then e to the negative 1 is t. That is my only critical number. Right? Don't forget that that can be written as 1 over e. All right. And that's it for you guys on this one. As you go through this, please, as always, let me know any questions that you guys have, and I will talk to you all soon. Bye.